Hello guys, I'm Stanley from Photoneo, and today I'm going to show you how to set up a beam picking solution in Beam Picking Studio in less than 20 minutes. I will be using this vision controller and picking this part with help of FoxEM scanner and UR5 robot. We'll begin while logging into our Beam Picking Studio. Username and password. Okay, I have a typo, no problem, just correct it. Alright, and it is it. I see a list of solutions and I'm going to create a new one from scratch. To show you, it is really easy. In the background it is loading its files into the database. It will take something like 10 seconds usually. I will provide a descriptive name, so it will be beam picking speedrun, for example. I'll omit description for now. The robot is actually Universal Robot UR5 and it is E-series. Inside the robot there is already a beam picking program, a simple program which will be executing functions like scan, get trajectory, execute trajectory, move to the placing position, and similar. For the gripper, I'm going to create a new one from scratch. It will be gripper speedrun. Maybe provide more descriptive name like vacuum gripper speedrun, and I'm going to open up CAD file of my gripper mounted on the robot, and here it is. Double check if the origin of the file is on the bottom, and yeah, it's good. I'm going to use it. To set up a tool point, I will use those arrows in here and move it to the favorable position at the end of the gripper, maybe round it up for 190 millimeters. Okay, it looks good to me as it is right now. You can see that the gripper is symmetric, so I'm going to enable rotation invariance in Z-axis and save it. Right now I have virtual 8 different tool points of my gripper. For the gripper I need to definitely select it. Vacuum gripper speedrun is what I'm going to use for the picking. Right, I have this green checkbox, so it is done. For the part, I need to set up some gripping points on the surface of the part, and it's a simple process, just like for the gripper. It is plastic T-fitting. Alright, insert CAD file and save. Similar to a gripper, a volumetric model is generated for collision avoidance. I can examine, okay, my model is correct, and hit the save button. For the gripping points, I'll choose my workpiece and I'll add a new set of gripping points via similar visualization. First of all, I'm going to rotate the gripper for 90 degrees, so I'm going to pick it from the side and maybe move it a little bit in this direction and this direction, so it is in correct position, something like this. This looks like a good position for a gripping. Also, this piece has a little bit of a symmetry itself, and I'm going to enable it, and I see it is an X symmetry, so this axis is loaded in here. I just need to move it using these arrows again to the correct position, to the center of the opening. And also, since I don't want to do a full rotation, just the half of it, I will limit the upper limit to 180 degrees. Everything else looks good to me, and this is what I have right now. 8 different gripping points, actually 9 different gripping points all around the surface of the plastic workpiece. Hit the save, just double check, okay, it looks good to me, going forward. For the grasping method, we have multiple path stages. These are waypoints which are generated during the path planning, and these waypoints are like a blueprint for the trajectory. We will begin in start waypoint, going through all of these, and end in end position. Start and position are loaded from the teach pen and they are saved positions. So what I can do is just to bind some kind of procedure to them. Detach procedure inside the robotic program is procedure which has digital output set to 0. So I release the gripper before I'm going to do a beam picking. The approach waypoint is first calculated waypoint, and it will take a grasping position, which is something like this, and will generate some kind of offset. I will use the coordinate space of my workpiece in order to generate this offset, and I'm going to set it to, let's say, 20 millimeters. It will be enough, 20 millimeters in front of the object, right? Something like this. If my object moves, this waypoint will be calculated on different place. And what I'm going to do as well is to enable attach right here, because I have a vacuum gripper, and vacuum gripper may be enabled in front of the picking. So I'm going to go with enabled vacuum to touch workpiece and literally suck it into a gripper. Save the position. Going to grasp. Since I enabled vacuum in approach position, I don't need to do anything else. Going to the approach position, and now the approach is the third one calculated. Actually, the grasp is calculated first, then the approach is offsetted, and the approach afterwards is waypoint, which serves as going out of the bin, something. Usually we use a robot coordinate system, or we use a fixed plane, which is basically XY plane, offsetted from the base of the robot by some amount. Since I want to remove the parts like 5 centimeters above the bin, and the bin is ending literally at the base of the robot, I just need to put offset value of, let's say, 50 millimeters in here. Very easy. And hit the save. So all of the parts will end up 50 millimeters above the base of the robot, which is in fact above the bin. And hit the save, and that's it. After the approach, we are going to end position. End position is transmitted from the robot program into Beam Picking Studio, so I don't need to do anything else. Inside the robotic program, the beam picking ends up in the end position, and then there are a couple of MoveJ commands which will just navigate the robot to the placing position, and that's it. So these are the picking path stages as a blueprint for path planning. Combined with the environment, they will generate a collision-free trajectory. The vision system part is used to bind together workpiece, scanner position, and some other parameters. So I'm going to create a new vision system. We can have up to 4 different vision systems per one solution. This vision system is loaded on the background. It will generate this form. I will put vision system. I will put the name for this vision system for T fitting. Scanner ID will be used. The scanner I have attached on the top of the robotic cell, which is 17090004, right? It is scanner M sized model, and it is based on the robotic cell. The picked object will be plastic T fitting, since I have only one, and I need to create localization profile. This is CAD based localization. So what is done on the background, the CAD file I uploaded into the beam picking is loaded into the localization SDK, and when I hit start locate, the localization is actually starting right now. And in a couple of seconds, the point cloud from the scanner was transmitted into the studio. And now I see the robot is blocking the view, so I'm going to move him. Just a little bit, so we can see a little bit more into the bin. Alright, now we have 42 parts in the first couple of seconds, and since nothing else was happening, I'm going to limit the timeout for 5 seconds only, so it will be not consuming all this processing power for that long duration. And also I'm going to enable bounding box, because I'm going to pick only from the one bin, not both. And I will rotate it just a little bit, also move it to the correct position, something like this. Maybe I can also resize it to avoid any false positives. Right now, when I hit start locate, you will immediately see it in action, since I have parts only in the left box. Oh yeah, it's actually right box, right hand side of the robot. Good, pretty satisfied with the result. Out of the box settings are good. There are more settings than just these 4, but they are running pretty smoothly out of the box, so I'm not going to change them right now. I'm going to save configuration, and once the configuration is saved, I will quit localization. Okay, and afterwards we have localization profile. We can set up collision sensitivity. This is a threshold, how much of the point cloud is noise and how much is actually colliding with the gripper. This is something you will fine tune after you run bin picking for a couple of cycles. And I will be using fast scan, which is using only 2-dimensional image, which is acquired in fraction of the second, to compare previous scans, and this can literally save you seconds from cycle time. Calibration metrics is pretty empty right now because we didn't do any calibration so far, but we are going to do one now. To start the calibration, I need to just select proper size of my ball, which is going to be used for calibration. And from the robotic side, I need to remove the bins and attach a ball to a gripper. Yeah, my ball is attached. And for calibration, I need to move robot to 9 different locations and acquire a full point cloud from those locations. Each step is recorded in the calibration process, so I'm going to repeat this 8 more times. Yeah, and I actually did one extra, unnecessary, but whatever. And we see a result now. A calibration matrix is filled in with some data, and we can also see a verification of our calibration, which is neat to see whether the calibration is really that accurate as it says. Right now it says it's 0.9 millimeters, and it definitely looks like it is that accurate. Yeah, there are a couple of points floating around for millimeter, but nothing spectacular. Otherwise it is matching pretty consistently the position of the robot. Okay, this was calibration in just a couple of seconds. I am satisfied, so I'm going to finish and save the results of the calibration. Put pins back into the bin, into the robotic cell, and move robot a little bit away. Okay. For the environment, for successful path planning without the collisions, we just need to upload a couple of CAD files, like robotic cell and maybe a wall. So I'm going to help myself with the scanner. Okay, I see point cloud in here, and now I can use it as a reference for moving all those CAD files in here. So it will be cell, robotic cell, and it is type environment, and I see it is rotated 90 degrees, so I'm going to rotate it. You can always use these sliders. Okay, also I see it is rotated a little bit in this direction, just 1 degree or such. Okay, this is correct position of my robotic cell. I'm going to add a bin, right? Yeah, and it's already in correct position, good. And also I'm going to add a wall behind, and I'm going to create one from the box, which is pretty simple. Just move it and extend it a little bit. Good. So this is my environment. Also I can create a new wall to actually guard me in here, so the robot will not touch me either. Right now the robot has limited space to move on, and this is basically it. I have finished environment, every single step is finished, so I can proceed to the deployment of the beam picking. When I try the beam picking first time, I usually lower the speed to some reasonable value, like 30 or 25%, just to see if everything was set up correctly. Then slowly increase the speed of the robot. So right now I'm going to start the program and see how it behaves. The scan was acquired and we see parts in the bin already, and also a trajectory which was calculated for the first part. Okay, you heard the vacuum, and it barely touched the part, so I know that I need to adjust the 2 point just a little bit, only a couple of millimeters closer to the part, so I won't miss it. open up the project, gripper, edit a gripper, 2 point, and move it a little bit closer. Like this. Save. It is always better to extend the 2 point and not pick at the first time, instead of, you know, going too close and damage gripper or the part. So I corrected that. And I am able to start deployment again. Cool, the beam picking is running, the scanner is connected, and start the program. Okay, I'm going to stop it in here. You can see it was super fast and super easy. Well, everything was running as expected. We created solutions from scratch. Yeah, I'm pretty satisfied with the results. Thank you again for watching. See you next time.